So the next problem example I'd like to do with you is from the same page as the previous ones. And again, if you don't have that page for whatever reason, you can just jot this problem down on a piece of paper and solve it along with us. It asks, if you start with 45 liters of ethylene, and there it gives us the formula C2H4, how many grams of carbon dioxide will be produced? Now, this is making some assumptions, this question. It's assuming you've got some oxygen laying around, because the classic trick question in chemistry would be one like this, and the real tricky answer would be to say, well, if you don't have any oxygen, then you won't make any carbon dioxide because you can't make this reaction happen without the oxygen. So you can assume that I'm not trying to be sinister and trip you up like that, and that there's plenty of oxygen around, because generally when we perform a combustion reaction, we're not too worried about the oxygen running out because it's kind of just all around us. So in this problem, let's assume that's the case. And let's assume one other thing, that we're working at standard temperature and pressure conditions, like I mentioned in class, because if we're not, then we can't solve it quite this easily. We'd have to use a gas law to make some adjustments. So when we assume that we're working at standard temperature and pressure conditions, that means that we can use Avogadro's gas volume constant, and that says that for every 1 mole of a gas at a standard temperature and pressure, it'll occupy a volume of 22.4 liters. We're going to use that value in this problem once, at least, at the beginning. And again, we have to assume that we're at standard conditions, or we can't just use that number. It's really handy that we can. So in this particular problem, as usual, we want to start out by balancing the equation. We have 2 carbons on the left, so we need 2 on the right. And we have 4 hydrogens on the left, so we need 4 on the right. And we can get those done by having 2 2's. On the right side now, we have 4 oxygens in the CO2 and 2 more in the water. That's 6 total. So a 3 on top of the oxygen, or rather in front of the oxygen, gets it done, and the ethylene gets a 1. So 1, 3, 2, 2, and we've got our equation balanced. Now, we're going to start out our stoichiometry again with whatever amount the problem gives us. In this case, that's 45 liters. Pardon my somewhat crooked line here. It's not as easy as on a whiteboard. So, I'm going to start with 45 liters of ethylene, and notice the problem doesn't give me much precision, just 45 liters of ethylene. So that's not only 2 significant figures that we've got there, which in the end will limit our answer somewhat. Let's keep that in mind when we get to the end and have to round. All right. So first step, as usual with stoichiometry, is balance the equation. We did that, and now convert the starting amount that you're given into moles if it's not there already. Well, it's not, right? 45 liters isn't moles, so let's convert it. Well, we know that 1 mole of any gas, including ethylene, C2H4, has a certain volume of 22.4 liters of C2H4 at those standard temperature pressure conditions that we're assuming this problem's written to be under. And so liters of C2H4 will cancel out, and I'd be left at this point, if I plugged it into my calculator, with moles of C2H4. We're not quite ready to solve it yet, though, because we have a couple more steps to go. The next step, again, is to relate the target substance. And again, look at my problem. It's asking me how many grams of carbon dioxide will be produced. How many grams of carbon dioxide? So this is the step where we'll switch over to carbon dioxide, and we'll get rid of C2H4. So in our problem, we want to bring our units, as usual, down and to the right. Moles of C2H4 comes down and to the right. And on top will go my target substance, the one I'm trying to get to in this problem. And again, that's my carbon dioxide up in here. So on the top, I'll bring in moles of carbon dioxide. And again, as always, the numbers that go in front on our mole ratio, which is that third set of boxes, or our second step in the actual math of this problem, are to bring down the coefficients from the balanced equation. So this equation says that 2 moles of carbon dioxide will be made. So I'm going to bring that 2 down right into here. 2 moles of carbon dioxide will be made for every 1 mole of C2H4 that I put in to the reaction. So 2 to 1. And it kind of makes sense, right? We can look at this and say, well, this is C2H4, and this is just C1O2, basically. So for every 2 carbons in my starting stuff, I can make 2 CO2s. And so a 1 to 2 ratio kind of makes sense. At this point, my units will cancel out, moles of C2H4, but I want to remind you of one other thing. Remember, when we're converting to moles or converting from moles, the first step here will always use a 1 mole conversion. 1 mole is 22.4 liters. And in the middle step, the 2 and the 1 in this case could be any whole numbers depending on the equation. And so, long story short, this 1 that we used to make the first conversion step happen, this one right here, doesn't have anything to do with the one that we've just written down here, right? And so as we go to solve the problem out, we're only really bringing along the units. Moles of C2H4 came down, and there's a 1 on the bottom in my step here because there was a 1 up in the front over here at the beginning of the problem in the balanced equation. So those 1s are just coincidentally both 1s. And I want you to always remember in that middle step, the 2 and the 1 could be any whole numbers at all. And as you do more and more problems, you'll see that all kinds of whole numbers show up. So as I go to cancel this out, moles of C2H4 will cancel out. And the final step is then converting the target substance or the ending substance, my carbon dioxide, into the desired units. Again, we can convert moles into grams, liters, molecules, whatever. In this case, the problem is asking how many grams of carbon dioxide, so I'll go ahead and do that conversion. And for our mole conversion to grams, we want to say that 1 mole of any substance, including carbon dioxide, has a unique molar mass that when we go to the periodic table we can add up. So to get grams of CO2, you're going to go to your periodic table and add up CO2. And altogether that should be 44 grams or so when you add that all up. All right? So moles of carbon dioxide will cancel. I've got 3 steps. I converted liters to moles in the first step. Second, I connected moles of carbon dioxide on the top to moles of C2H4 on the bottom by saying that in this reaction, for every 1 mole of C2H4 I put in, I get 2 moles of CO2 out. And finally, I converted the moles of carbon dioxide into grams of carbon dioxide by saying that there are 44 grams of CO2 in 1 mole of CO2. And that was found by adding it up off the periodic table. Now, if you go to punch this into your calculator, it'll give you something like 176.8 grams of carbon dioxide. But again, keep significant figures in mind. Turns out that at the beginning of this problem, we had 45. 45 only has 2 significant figures. And so when we round our answer at the end of this problem, it should only have 2 significant figures as well, while 176.8 has 4. It's way too many. So we need to round that off to have 2 significant figures. How would we do that? How would you make 176.8 have just 2 significant figures? Hopefully you look at that and you say you could round it off to 180 grams of CO2. And as long as you don't put a decimal point in there, which you shouldn't anyway, because you're rounding to the nearest tens place, that would have 2 significant figures, 180 grams of CO2. So for every 45 liters of ethylene you put in, you would get 180 grams of CO2 out. We could have solved for liters at the end, we could have solved for molecules. This particular problem asks us to solve for grams of carbon dioxide. And in each purpose, or rather in each problem, there's a different purpose for the different units involved. We don't always have to know or care what those are, but just to practice the different ways of solving for whatever units the problem asks you for. So that's a couple of examples. Hopefully you already watched example problem 4. This is example problem 6. Continue working on, if you're again working off the sheet that I provided in class, continue working on as many of those as you can comfortably in the time that you have until we're back together again, and we'll check over answers then. Thanks a lot, and we'll see you then.